Well, hi, everybody. In this video, I'd like to show you an application to the real world of some of the stuff about differential equations that we've been studying. In particular, one of the most important types of differential equations is a first-order linear differential equation. And it turns out that one of the physical applications that I've talked about in an earlier video is first-order linear, namely mixing problems. Okay, the differential equation for mixing problems is something that I've talked about previously. And here it is on my board right now. dA dt, this is the rate of change of the amount of a chemical with respect to time, plus R2 over V times A equals R1 C1. This is the sort of North Star of this video. This is the key equation for this video, the first order differential equation. And it's linear. It is actually linear, as I'll show you when we start plugging the numbers in. Might be a little hard to see, but I just redrew a picture of this tank that has this chemical dissolved in the solution here, and there's A of t amount of chemical at any given time. It's a function of time that we would like to solve for. Flowing into the tank, there is an inflow rate and a concentration of chemical that's pouring in through this faucet. And at the same time, there's also a leak at the bottom of this tank. And the rate and concentrations of stuff leaking out is given right here, R2 and C2. So I'd like to take all of this and put it into a real problem now. Feel free to pause this video if you need to take a minute to write down this word problem. This is the problem I'm going to solve in the next few minutes. What we're looking at here is a tank with a lot of information about it. It starts off with 600 liters of a solution, and in this solution, we're going to assume initially that there are 1,500 grams of salt that are dissolved in this solution. Now, pouring into this tank is a stream of chemical that has 5 grams for every liter that flows into that tank. And let's assume that this faucet is turned on with a speed that delivers 6 liters every single minute. So you can see that every single minute there will be, 30 grams of chemical delivered every minute into this tank. At the same time, the mixture leaks out at 3 liters per minute. And so I put together a question: how much salt is in the tank after 1 hour? I think it's very important that we start off by figuring out which numbers in this question go with which of the variables in the equation. And I'm going to actually write them down over on my board on the right-hand side. If you'd like to try it for yourself, just pause the video for a few minutes, write down what is R1, what is C1, what is R2, what is V, right? So that we can actually start plugging things in to our differential equation. Well, the R1 in this problem is the rate of inflow to the tank, and that's given right here, right? 6 liters per minute. That's how fast the faucet is pouring the solution into the tank. And of course, R2, which is the outflow rate, it's leaking out at 3 liters per minute. And then the concentration flowing in, that's C1. And see, I need all of these numbers, don't I, for my differential equation. The C1 is the concentration that's flowing into the tank. That's 5. Okay. We also need the volume right here. I'm just going to remind you that the volume, maybe I can put it down here. When I talked about this in another video, I wrote down the volume. The volume is some initial volume plus R1 minus R2 times T. So this is actually another equation that we should try to make sure we know. But we can see the initial volume is 600. And so I can write down the volume here is 600 plus R1 minus R2, 6 minus 3 is 3, times T. And those are the key ingredients that we're going to need in order to write down our differential equation. I will mention, however, that there's another number here that we haven't put on the board yet, the 1,500 grams. That is simply the initial amount of chemical. At time 0, what is A of 0? In other words, this is actually not just a differential equation. It's actually an initial value problem, right? Remember, an initial value problem is just a differential equation together with an initial condition. So we actually do have an initial condition right here. A of 0 equals 1,500. Let me take the differential equation and start plugging things into it now. Okay, so we've got all the numbers written down. Let's see what we can do. dA dt plus R2 over V, that would be 3 divided by 600 plus 3T, that's times A. And then R1 times C1 is just simply 6 times 5, which is 30. Just to make our life a little easier in a few minutes, what I'm going to do is actually divide this fraction here. You see this fraction? There's factors of 3 everywhere, right? So I'm just going to divide everything through by 3. So this will just simply reduce to 1 on top and 200 plus T on the bottom. And this is equal to 30. Now, guys, this is actually just a linear differential equation. You might remember when we talked about linear differential equations, there was always a P of X and a Q of X. And we've got those here, but they aren't functions of X in this application. I want to think of them as functions of T. So P of T and Q of T. However, this is, regardless of what the letters are that we're using, this is linear. This is a linear differential equation right here. And so we've learned how to solve these things by using integrating factors. We have an integrating factor formula, which is e to the integral of p, in this case it's p of t dt. So let's plug this in and see if we can solve for I. We're going to have to integrate up here 1 over 200 plus t. When you integrate 1 over 200 plus t, you actually just get the ln of 200 plus t. And e will cancel the ln. We actually will just get 200 plus t for the integrating factor. Now, some of you may remember that when we actually integrate with the natural logarithm, we're supposed to put absolute value bars around the expression. However, this is a physical problem where t is going to be greater than 0 for sure. So 200 plus t doesn't really need absolute value bars because it has to be positive already. And so there's no need for us to do any more with that. Okay, great. So we have the integrating factor. And so let's come back over here and write the resulting product rule derivative that we get out of this process for solving a linear differential equation. So we get the product rule derivative of the integrating factor times the unknown function is equal to the right-hand side, which is the Q, that's equal to 30 in this problem. And we've now multiplied that by 200 plus t. I think it's going to be helpful. It's not really necessary, but it might be helpful to actually just go ahead and multiply out the right-hand side. We get 6,000 plus 30t. And now I'm just simply going to follow the process for solving a linear differential equation. I will now integrate both sides. So I'm going to integrate right here. That'll give me 200 plus t times a on the left side. And on the right-hand side, these are not hard things to integrate. 6,000 is just a constant, so we'll put a t next to that. And then when I integrate 30t, I get 15t squared. And then I need my plus c as well. Okay, guess I'm going to erase a little bit here. Come back up to the very top to wrap this up. When I solve for a, I just simply have to now divide by the integrating factor, which was 200 plus t. And the rest of the numerator is just what we had before, 6,000t plus 15t squared plus c. This is the amount of chemical at any time t. Take a breath. Feel free to slow down if you're taking notes and want to stop and make sure you're following along here. That's perfectly a good thing to do. This is what we would call the general solution for A of t. But of course, I do have an initial condition. I managed to keep it on the board right here. When I plug in 0 for t, A is supposed to equal 1,500. Let's take advantage of that to see if we can solve for c. Okay, because again, just to reiterate, this expression up here is called the general solution. But when you have an initial condition, you can actually get a particular solution where the c doesn't appear any longer because you can actually solve for c. So what I'm going to do right now, I'm going to put in 1,500 for the A of t part, and everywhere on the right-hand side, I'm going to put t to be 0. And what I will notice is the only things that don't disappear are the c on top and the 200 on the bottom. When you simplify that and solve for c, you actually are going to get a 3 with a lot of zeros behind it. It should be 300,000. All right, and so my particular solution would simply be 6,000t plus 15t squared plus 300,000, all divided by 200 plus t. This is A of t. This is the amount of chemical at any time t. Now it asks over here, what is the amount of salt after 1 hour? So that would just simply be 60 minutes. Be careful with the units here. Everything up to this point has been calculated with the use of minutes. So when I have 1 hour in my question, I would rather change that to 60 minutes. And we just have to evaluate this. 6,000 times 60 plus 15 times 60 squared plus 300,000, all divided by, I guess that's going to be 260 by the time I put in 60 for t. And I don't actually have a simplified answer for this, I'm sorry to say, but this is perfectly reasonable without a calculator to kind of leave an expression in this format. I don't really mind at all. We've got the general solution, or I'm sorry, the particular solution right here, which is really the most important thing for my purposes. And if we now plugged in t equals 60, it would look like this expression, and I would need a calculator to come up with a final answer, but that's not so critical to me. Another nice application of linear differential equations to mixing problems, and I hope it's all making relatively reasonable sense to you. If there are questions, I hope you'll write them down. I hope you'll reach out to me and let me know so that I can try to help you clear things up. Otherwise, I will look forward to giving you some time to digest this and think about it, and see you guys all again very soon. Thanks a lot. Take care. Bye for now.